Good? Oh, yeah. Cool. Good morning, everyone. My name is Gabrielis. I come from Uni of Edinburgh. And I'll talk to you this morning about sort of where we could use and where we couldn't or shouldn't use AI in computational design. Sort of give a bit of an overview, a bit of my own perspective where I think we could use it, where we couldn't use it. So I'll start with a slide about myself. I come from a mech eng background. I did my PhD in design optimization, AI, and mechanical metamaterials. So sort of very much along the lines of what a lot of you people do here. And now I'm working at the university looking at how we could use sort of computational methods and apply AI in energy and energy material sectors, sort of modeling energy structures and materials. So, and today I'll just start talking about mechanical metamaterials because it's CDFAM, and we all love lattices. And then I'll move into how similar concepts can be scaled up, and how can we design wind turbine blades, and then move on to surrogate models and sort of last slides about sort of discussing what Duan mentioned. Can AI solve our problems, or can it not? Or more like, where can it work and where it can't work? Cool. So, because it's 9 a.m. in the morning and you're all geometry geeks, I thought, why not overcomplicate things and talk about four-dimensional polytopes? Good morning. So they are these very interesting structures, at least to me, that have geometrical similarities with fractal structures. So if you look top right, you probably see you see that nice structure there. That's a fractal structure. Basically, the beauty of it is if you zoom into it, it has geometrical repetition with every zoom-in level. And four-dimensional polytopes actually have some very similar properties to that. So just a bit to demystify it, you probably heard about a tesseract. That's what you see there on the right. And sort of how it is built up, it's if you look in one dimension, you would just have a line. In 2 dimension, you would have a square. 3 dimension, you would have a cube. And in 4 dimension, you would have a tesseract. The only problem is, well, you can keep on going like this because these are sort of mathematically defined geometrical structures. And you could have 5th dimension, 6th dimension, and so on and so forth. So that's all the mathematical tier that I'm going to give you today. But basically, the issue here is a 4-dimensional structure. We live in 3 dimensions. The closest to the 4th dimension that we have is time. We can say that time is the 4th dimension, and we just sort of, represent that 4th dimension as time. And you get something like this. You get your 4 polytopes as projections in 3-dimensional space with time. So if I now tell you that, I could use these to make metamaterial unit cells or like lattice unit cells, you can probably see that, I can take a snapshot and create lattices for each rotation of the structure. And going that we're at CDFAM, sort of what would you do next? You would build that up. You would build simulations, right? You would build elastoplastic fracture mechanics models in this case. You would run thousands of simulations to sort of try to see what would be mechanical properties or where we could go with that. And in this case, I sort of settled down on optimization objective to maximize stiffness while minimizing weight. So basically lightweighting the structure. And of course, as most of you do it here, the next stage is manufacturing, so 3D printed. And basically we had developed sets of these metamaterial structures for compression, tension, shear. And if you want to know more about it, there are publications at the top. Perfect plug for my research. And then, of course, you do mechanical characterization. You see how it fits with other structures. And the only thing that I would like to get your attention on, like a lot of people do gyroid, and then you ask them, why do you use gyroid? They don't know. So if you're using gyroid for mechanical properties such as stiffness or strength, this is where gyroid sits. This is where all the other structures sit. I mean, again, I'm not saying go and use these structures, but think about what you're using. But basically this problem that I described to you, you generate a structure, run simulations, run optimization, and so on, can be, that optimization problem can be defined as looking for a Pareto front, especially if it's a multi-objective optimization problem, right? So I said stiffness and light weighting. So basically you explore your design space with different variations of the structure. Then you draw your Pareto front, and then you look for the point that is closest to your ideal point. This is just basic optimization, right? And you do, I don't know, genetic algorithm for that, or particle swarm, or whatever you want to use. But you get the idea, right? So the idea of this is your like forward design problem, right? You start with some design parameters, and then you sort of get through your simulations optimization to arrive at your performance measures, right? And it's very good, but it's sort of very computationally intense. So I sort of asked myself this question: could we do it otherwise? Could we do it the other way around? Could we do the inverse problem? Sort of tell your framework that these are the properties that I want, and ask it to sort of generate structures that best suit that type of application. And this is where actually my sort of dive into AI, ML, and at the moment NLP sort of started. I sort of went through literature and sort of a little bit like weeded out what works, what doesn't work, what people use, because inverse design problems are not new. People are using it, but there are different ways to approach it. So yeah, looked at anything that falls in the umbrella of artificial intelligence for design specifically of mechanical metamaterials and lattices. If, again, another plug, if you want to know more about it, there's a paper. The only thing that this came out in February, and we were talking with Duan, like maybe we could maybe I could present on this. Since then, there's a new sort of trend of using large language models for optimization. So this is basically what your ChatGPT runs on. So imagine when you're putting your prompt in, imagine that as an input for your optimization problem. So again, if you're interested in this, I highly encourage, read my paper and then look at that stuff, because that's groundbreaking at the moment, I think. Okay, and now about the big structures. So this was all work on mechanical metamaterials, small scale. And then at the same time, we had a company approach us, TAF Composites, really brilliant guys there. They work on sort of composite materials, renewable energy applications, and that moment they were looking at how could you redesign a wind turbine blade. And their problem was this. They were saying, could you make it lighter? And why do you want to make a wind turbine blade lighter? It's pretty straightforward. They're getting bigger with every year, with every iteration. And because they're spinning around the hub, one of the main loading conditions there is, one of the main failure modes are fatigue loading. So the higher the weight of the blade, the higher the fatigue loading, and the shorter the lifespan. So if you could actually reduce the weight, you could make them last longer, theoretically. So we looked into how could we sort of lighten the structural components of the blade, and the structural components are the same as an aircraft wing. You have like a spar box. So usually these days, carbon fiber spar caps, top and bottom, and then the sort of shear webs holding that whole box geometry together. And that geometry, of course, at the hub is circular. Later on, it's sort of to match that aerofoil shape changes and all of these changes. So the point number one, geometry is varying along the radial location of the blade. Point number two, the blade is actually not experiencing a uniform distributed load. It's seeing something like that of a loading profile in an edge direction, in a flap direction, in the edge direction, you have another loading profile. Again, bottom line, geometry is varying, loading conditions are varying. So if you're trying to optimize something like this, you're looking at a problem where for every radial location, you would have to have a different structure. If it's a lattice, then different optimized lattice structure at each location. And I don't know if I mentioned the blade is 120 meters long. If you want to do it as a granular level and think of the number of finite element mesh, sort of, yeah, number of elements that becomes crazy. I know guys from DTU in Berlin were talking about doing topology optimization on wind turbine blades, and that's very great, but you need a supercomputer, and you probably need a month or 2 months of computational time on that to solve that type of problem. So I didn't have a luxury of that, unfortunately, so I sort of went and looked into how else could we approach this problem, how could we optimize for every location along the blade, but sort of don't break the bank at the same time. And we built like basically an artificial neural network model that was trained on a sort of lattice library, which helped with this inverse design problem. So we have had library of lattices, we trained our model, and then we said, here are the loading conditions for this blade, here's the sort of geometrical constraints, predict or sort of give me your best solution for each location. And that really, really saved a lot of time. It didn't necessarily give us the final solution for what lattice geometry could be, but it very much, offloaded a lot of computational work. And this is what I'm allowed to show you without revealing too much, but basically we made a sort of lattice-looking design for that spar box that sort of replaces it, and that yielded like a 27% weight reduction while keeping the same mechanical properties. So, of course, like final refinement of these lattice structures were done again like the forward design way. So we sort of did the final tweaks the old-fashioned way, but ANNs can really do things much quicker by just predicting things, and it worked very well in this case. So, and I guess there's a couple of ways of doing it. The way we did it in that problem was we use a just simple model architecture like artificial neural network. Now there's more and more rise of graph neural networks, and the beauty of those are that the way the neurons are positioned, they actually capture the geometrical intricacies of your lattice or of your structure, and basically that drives the accuracy up. So if you're looking into something like this, come either speak to me or look into this, because this is, I think, very interesting. And I'm sort of at the moment continuing similar work within one of our research facilities. So this is Fast Blade. It's a tidal turbine blade, not wind turbine, tidal turbine blade testing facility, where you have, it's probably the size of this building of New Lab, and then you walk inside and there's like this massive green pencil sharpener looking like frame into which you mount your tidal turbine blade. You put hydraulic ramps here underneath, and you basically try to break it, mechanical testing. And so what we do now with that is we run digital twins, we run surrogate models, we try to predict how will those composite structures break, what delamination you'll get, and so on and so forth. Cool, so now to the last part, sort of summarizing a bit, like where AI works and where it doesn't. And again, this is my perspective, this is my opinion. If you disagree, come, let's speak. So it's, first of all, it's not a silver bullet. It doesn't work for everything. It's not going to solve all your problems. I think the way to think about it is that these are predictive tools. And they're very good at predicting, but they will never, in my opinion, replace like traditional PD solvers, FE solvers, sort of direct optimization. But I don't think we shouldn't try to replace them. We should try to, if you have a bunch of simulations that you run, use them to train that AI model to mimic that behavior, and then do sort of maybe something like what I did, like try to reduce the computational time, like take a shortcut with AI, then so you could later on refine it, but I would say don't expect it to solve all your problems. And then, of course, like as with any tool, you have limitations, right? So data availability is always key. AI is nothing without data. If you don't have anything to train it on, then that's it. So it works much better for sort of repeated problems or problems that are similar to what you solved before. Of course, we have this whole causality relationship problem. Those are black box models, so they need to be tested, validated, and whatnot. But as I said, in some cases, like designing these structures, it still offers like a massive time saving. And then, we're moving more and more, like we hear about like models hallucinating and producing, like, again, if you look at it as a predictive tool, then it's not that surprising. Weather forecasts also hallucinate. So that, but I think it's getting better and better if you get better and better training data. And then a lot of work, at least in my circles, now being done on generalization. So how could you move, if you trained one model, how could you transfer some of that knowledge to something else? Okay, so this is my last slide, and basically these are the summary bullet points. So I would say don't use AI to replace direct methods, but rather use it to enhance them. And don't look at exact solutions, but rather aim to reduce computational time. Look for shortcuts that AI can, or ML can offer you. And as with any other tool, go and try it out. If you're working on something similar, come speak to me. Let's have a chat. But sort of be wary of its limitations, because AI at the moment is on that peak. It's gonna reach plateau, but I don't think it's yet now. So it's oversold, but let's not overlook what it can actually offer. So thank you very much. That's me.